Welcome to iLecture Online, and here's some examples of how to work with torque in static problems. So static problems are where everything is motionless. That means there's no net forces in any direction, and that means there's also no net torques in any direction. And that's very important when we do problems like this, where we have to use the concept of torque to find the solution. So here we have a vertical pole. We have a beam attached to the pole that is able to pivot like this. We have a cable keeping it from moving like this, and then we have a mass hanging from the very end of that beam. Now, the problem here asks to find the tension in the cable. In order to do that, we have to pick a pivot point, and I'm going to pick my pivot point right over there. The reason why I pick it there is because I have no idea what the forces are on the beam on this part of the problem, so that by putting a pivot point right there, it eliminates any forces going through the pivot point as being non-material to the problem. All right, I'm going to label that pivot point number 1, and so I can say, based upon this, that the sum of all the torques around pivot point number 1 must add up to 0. And so now what I have to do is identify all the torques related to this problem relative to that pivot point. So using a different color pen, I can say that definitely I have a force going in this direction, and that pen doesn't work very well anymore. So let me use a different color. I think my blue pen is still working. Let's try that. There we go. So where we have the mg, the weight of this object, going down like that, and of course the distance from the line of action of the force to the pivot point, the perpendicular distance right here, could be considered d1. So this would be d1, which is the distance from the line of action of this force to the pivot point. Now, the big beam has a big mass, so the center mass would be right at the middle like this, and we have a big mg, which is the weight of the beam, acting through the center mass of the beam, and the distance from that line of action of that force to the pivot point, I can call that d2. And then finally, we have a third force here, which is the tension in this cable right here, which pulls in this direction. If it didn't, the whole beam and this mass would just simply fall down. So there's a force going in this direction. So this is the line of action of the force, and this is the perpendicular distance from the line of action to the pivot point right there, and I can call this here distance d3. Now notice that these two forces, big mg and small mg, would cause this beam to rotate in this direction. The tension of the cable would cause the beam to rotate in that direction if those were the only forces acting on the beam. So by definition, I'm going to call clockwise a positive torque, and I'm going to call counterclockwise a negative torque. That's completely arbitrary. I know some textbooks do it the other way around, but this is the way that I'm used to using it. So, and again, it makes no difference as long as you're consistent within the problem. So what we're going to do now is we're going to sum up all the torques, and again, by definition, a torque is equal to the force acting on an object times the perpendicular distance from the line of action of the force to the pivot point. So make sure we remember this definition of torque. So let's go ahead and add up all the torques. So first torque is the mg, which is acting in this direction. So since it would cause the beam to rotate in a clockwise direction, if this was the only force acting on the beam, it's a positive torque, so it's plus the force mg times the distance, the perpendicular distance from the line of action of the force to the pivot point, which is d1. I like to just first do it visually, and then later on figure out what the d1, d2, and d3 are equal to. Then I have a second force, which is acting this way. Again, if this was the only force acting on the beam, it would cause it to rotate clockwise. So it's a positive torque, positive mg, times the distance from the line of action of force to the pivot point, which is this distance d2 right there. And finally, I have the torque, not the torque, but the tension in the cable that would pull the beam in the opposite direction. I'm going to call that a minus torque, minus tension, times the distance d3. Now, I denoted that the beam had a mass of 200 kilograms. The weight at the end had a mass of 50 kilograms. I did not say yet what the length of the beam was, so just imagine that the length of the beam is equal to 4 meters. All right, because we need to know that. Maybe not, we'll see. All right. So, what is the tension on that string? Well, here's our equation. It's set equal to 0, so let's plug in what d1, d2, and d3 are equal to in this particular case. So 0 is equal to mg times d1, and d1 is equal to the length of the beam times L, plus big mg times d2, which is half the length of the beam, which is L over 2. And then minus the tension times d3. Now what is d3 equal to? It's this distance right here. Now this distance here makes up a right triangle here, makes up this triangle right here. So let me draw this triangle out here on the side. So this is distance 3, d3. Then we have the part of the cable coming down here, and this is the length of the beam. This is L, and that's a right angle. And this angle here is theta, and theta was equal to 30 degrees. Now notice, let me get rid of this piece right there. Notice that d3 is opposite to the angle. This is the hypotenuse of this triangle, so I can say that d3 is equal to the hypotenuse L times the sine of the angle theta, because it's opposite to the angle theta, so therefore the sine of theta will define d3. So I can then plug in what d3 is equal to. It is equal to L times the sine of theta. Now since this whole thing is set equal to 0, notice I can actually divide both sides of the equation by L. We didn't even need to know the length of the beam. So L, and L simply cancels out because the whole equation has an L in each term and it's set equal to 0. The next thing I'm going to do is move the component that has the variable I'm looking for, which is the tension here, to the left side of the equation. So we have T times the sine of theta is now equal to mg plus 1/2 times big mg. And finally, I'm going to divide both sides of the equation by the sine of theta. So that the sine of theta here cancels out, and I have the tension here is equal to the little mg plus 1/2 times the big mg, all divided by the sine of theta. And now I can go ahead and plug in the numbers. So tension is equal to little mg. Little mg is 50 kilograms times 9.8 meters per second square, plus 1/2 big mg. Big M is the mass of the beam, which is 200 kilograms, times 9.8 meters per second squared. And the whole thing divided by the sine of 30 degrees. And the sine of 30 degrees, I believe, is 1/2. So, where's my calculator? Here we go. So we have 50 times 9.8 plus half of 200 is 100 times 9.8. And we divide that by the sine of 30, which is 1/2. And the tension in that cable is equal to 2,940 newtons. And there you go. That's how you do a torque problem like that. If this was confusing, I'll come up with a few more examples for you to take a look at. But at least that's a very good, straightforward example. And after a while, I think you get the hang of it, of how to go ahead and solve these kinds of problems. So let me do a few more examples.